Distributorless Ignition. Part 1. Point Type System. The automobile has been part of our lives since the Model T rolled off the assembly line and appeared on the road at the beginning of this century. Since that time, there have been countless improvements in the comfort, performance, and reliability of the automobile. However, the gasoline engine, while vastly improved over years of development, still relies on the ignition system to ignite an air-fuel mixture in its cylinders. In this program, you'll be introduced to the most recent ignition innovation, the distributorless ignition. But because today's technology grows out of the past, you'll need to take a look at the evolution of ignition systems, beginning with the system that did the job for over 40 years, the breaker point ignition system.
To begin, let's look at how an engine works. An internal combustion engine generates power by burning an air-fuel mixture within the combustion chamber. Burning or combustion is one part of the engine's continuous four-stroke cycle. This system is based on the fact that gases expand when heated. Combustion, by burning or expanding the air-fuel mixture, pushes the piston downward in the process, creating energy to move the car. An important aspect of engine operation is that combustion requires a high-voltage spark to ignite the air-fuel mixture. The key function of the ignition system is to provide this spark. However, the ignition system's power source, the battery, only supplies a potential of about 12 volts. This low voltage is not enough to ignite the air-fuel mixture. The main role of all ignition systems is the transformation of this low voltage from the battery to high voltage at the spark plug. In cars with a breaker point system, a spark of about 20,000 volts is required to ignite the air-fuel mixture.
In this program, you'll be looking at how breaker point ignition systems perform three major functions: step up or increase voltage from the battery, deliver that voltage to the proper spark plug, and time the delivery of the spark in the combustion chamber. Early breaker point ignition systems, while varying according to design and operation, share many similar components and operating principles. These components and principles are important because they have evolved into today's electronic and distributorless systems. To begin, let's take a look at the components of the breaker point system. This system is composed of two basic circuits: the low voltage or primary circuit, which operates on battery voltage of about 12 volts, and the high voltage or secondary circuit, which generates about 20,000 volts.
The primary circuit consists of the battery, the ignition switch, an ignition resistor, primary windings of the ignition coil, and located within the distributor, ignition or breaker points, and a condenser. The secondary circuit consists of the secondary ignition coil windings, the distributor cap, the rotor, and the spark plugs. Inside the distributor is a rotor that spins because it's connected to the engine's camshaft by a gear at its base. Camshaft and rotor alignment are designed to ensure proper engine timing.
Now, let's look at how these components work together to provide an ignition spark to the combustion chamber. When you turn the key to start the car, current flows to and activates the starter or cranking motor. At the same time, battery current flows into the primary ignition circuit. The starter motor gives the engine enough power to move the cylinders until combustion takes over. But how does the ignition system convert this low battery voltage entering the primary circuit to the high spark voltage needed for combustion? To answer this question, you must first understand the concept of electromagnetism.
Scientists have discovered that if an electrical current is sent through a wire, a magnetic field will develop around the wire. Not long after, it was also discovered that this principle works in reverse. That is, if you move a wire through a magnetic field, it will create or induce a current flow in the wire. This principle of electricity became known as induction, or the ability of a moving magnetic field to cause or induce an electric current in a wire without any physical connection. It's this principle of induction that's used within the ignition system to convert low battery voltage to high spark voltage. The device that uses induction to increase voltage in an automobile is called an ignition coil. Let's look at how induction works in the ignition coil.
The ignition coil contains two sets of windings. A primary set, which consists of approximately 200 turns of relatively heavy wire, and inside the primary windings, a secondary set, made up of about 20,000 turns of extremely fine wire. Here's how the primary and secondary windings use induction to step up voltage. When the breaker points close, an electrical circuit is completed and battery current flows into the primary windings of the coil. This flow creates a magnetic field around the primary windings. However, when the points open, the circuit is broken and the magnetic field suddenly collapses. The collapse of the magnetic field induces high voltage in the secondary windings. The length of time the points remain closed is called dwell. The amount of dwell required to build a sufficient magnetic field is known as saturation time.
The difference in number and thickness between the primary windings and secondary windings produces voltage of a high enough level to generate the spark required for combustion. This increase in voltage in the secondary windings results in a decrease in current. The ignition coil transforms the high current but low voltage flowing through the thicker windings of the primary circuit into a low current but high voltage flow through the thinner, more numerous windings of the secondary circuit. It's this trade-off of current for voltage that is essential to generate a spark in the combustion chamber. It is the opening of the primary circuit and subsequent collapse of the magnetic field in the primary windings that creates high voltage in the secondary windings. This cycle from low voltage to high voltage spark will repeat more than 100 times per second in a running automobile.
Now that a high voltage is generated, it must next be directed to the proper spark plug. This stepped-up voltage, up to 20,000 volts, flows from the ignition coil into the center tower of the distributor cap. Here, the turning rotor connects the high voltage with the correct spark plug tower. At the instant the rotor makes contact with the spark plug tower, the voltage passes through the spark plug wire and into the spark plug's center electrode. The high voltage then jumps the air gap between the plug's center electrode and side electrode, creating the spark that ignites the air-fuel mixture.
A key feature in efficient engine operation is ignition timing. As engine load varies, it becomes necessary to alter the time at which the spark is delivered within the combustion stroke. By adjusting spark delivery within thousandths of a second, combustion timing can be varied according to driving conditions. Let's look at the components that adjust timing in a breaker point system. On a breaker point system, spark delivery is varied in two ways. The vacuum advance mechanism, a round metal canister located on the side of the distributor, mechanically adjusts timing in reaction to a measurement of the intake manifold vacuum. and the centrifugal advance, a device consisting of weights, springs, and a cam assembly which reacts to increased engine speed by mechanically advancing spark delivery. The vacuum and centrifugal advances work together to provide improved economy at low speeds and high engine output at higher speeds by varying ignition timing based on engine load and speed. Now let's review the key segments of this program. 1. All ignition systems transform low battery voltage to high spark voltage.
2. Breaker point systems use a rotor to direct the spark to the right spark plug.
3. The breaker point system adjusts timing with vacuum and centrifugal advances. This concludes an introduction to the breaker point ignition system. Even though it hasn't been used on automobiles since the mid-1970s, the concepts on which it's based provide the basis for understanding today's modern electronic ignition systems. In the next program, you'll see how a transistorized ignition module replaced the breaker points in the electronic ignition system.